Okay, so we're going to look at projectile motion now. We're going to look at an example that has lots of different parts. So you can think of this as one unified example, or you can think of it as lots of separate examples. But look at how we approach these problems, because you're going to see the approach is applicable to many other kinds of projectile motion problems. Okay, so here's the problem. A projectile is launched off of a 100-meter high cliff at an angle of 75 degrees with respect to the horizontal, that is the x-axis, and it has an initial speed of 20 meters per second. So here is my drawing. I have drawn my x and y axes, and I've put the origin where the thing is launched from. Here's my v naught, it's the initial velocity, and I've broken it down into x and y components. You can see that we know that v naught x is going to be v naught times the cosine of theta. So v naught x is the one that is the adjacent side, so that's why it goes with cosine. And then v naught y is the opposite side to the angle theta, so that's why v naught y is v naught sine of theta. Both of these components, v naught x and v naught y, are positive, we can see from the picture. And so we know a lot about the problem. That the cliff is given to be 100 meters high. Now, one thing that you'll notice here is that I've labeled here negative 100 meters. That's because the origin is placed at the top of the cliff. And so if we go down to the ground below the cliff, the position in the y direction will be minus 100 meters because you're below the origin. So anyway, that's what we're given in the problem, and let's look at what the problem is actually asking for. So as I said before, this problem has many parts. We want to find the time it takes to reach the maximum height of the projectile, that is the maximum height of the motion. We want to find what the actual maximum height is. So in part A, we want to find how long it takes to reach the maximum height. In part B, we want to find out what the maximum height is. We want to find out how long it takes for the projectile to reach the ground that is 100 meters below the cliff where the projectile is launched from. And then finally, we want to find the velocity with which this thing hits the ground, and also the horizontal range, that is, how far along the x direction does this guy travel. So this guy's coming up, it's traveling on some kind of arc, it's going to hit the ground some distance away from the edge of the cliff. How far in the x direction will it strike the ground 100 meters below? Now, before you go on with the rest of the video, I want you to do something for me. I want you to write down everything that you know in this problem. So, and you know a lot. You know the initial position, you know the final position, you know the acceleration, you know the initial velocity with its x and y components. You know what the magnitude of the initial velocity is, that 20 meters per second. You know the angle, you know the height. So write down, pause the video, draw this picture, and then write down a list of everything that's known. No, seriously, do that. Pause the video for just a minute and write down everything that's known in this problem. So let me recap what I've done here. The first thing I did was I draw a picture, and on my picture I put all the givens. And you have to think about things when you're given a problem, because very often you know more than you realize. So for example, if you're given an initial velocity and an angle, you can figure out what the x and y components of that velocity are using trig. So those are things that you know. And so realizing what parts of the problem you need is something that comes with practice, but as you write down the kinematics equations, you'll just find what things are given in the problem that you know and use them to customize those equations like we talked about in a previous video. Once you have those kinematics equations customized, it's like a puzzle. You have a bunch of knowns, you have some unknowns, and you have some equations which relate the things that you know to the things that you don't know. So you just have to figure out which equations are appropriate and apply them. Now, I'm going to show you how to work all these different projectile problems using the first two kinematics equations, the one for velocity and the one for position. And generally, our approach is going to be all about finding the time. So either you're given the time or you know the time and you can just plug it in, Or if you don't know the time, you will have to use one equation to find the time and then plug that time into a different equation to solve for whatever you're looking for, whether that be a position or a velocity or an acceleration or whatever. Okay, so I asked you just a bit ago to write down everything that we know about this problem. So here's my list of some of the things that we know. We know that the initial x and y positions are 0. We know that because I put my coordinate system with the origin of the coordinate system right where the thing was launched from. And we know the x final position is unknown. We're asked in the problem, how far away the projectile lands. We don't know what that is. But when the projectile lands at the bottom, we do know that the final position is minus 100 meters. Now, in another part of the problem, we were asked, how high it went and how long it took to get there. We don't know any of those things yet, but I did note that we know the final position for that last part of the problem, so that's something that I wrote down. We know the x component of the initial velocity is v naught cosine of theta, and we can go ahead and calculate that because they told us that the initial velocity was 20 meters per second and that it was an angle of 75 degrees. So if you plug that into your calculator, you'll get 5.2 meters per second, and that's the x component of the initial velocity. V naught y is v naught sine of theta. Again, that's the y component of the initial velocity. And we can plug in the 20 meters per second and the sine of 75, and we get that the y component of the initial velocity, that's that y component of the initial velocity, is 19.3 meters per second. And then finally, we know the acceleration, there is no x component to the acceleration, it's all vertical, but we do know that the vertical component, or the component along y, is minus g, or g in the minus y hat direction. Now, we have our generalized kinematics equations for x and for y, both velocity and position, and we spent a lot of time talking about how to customize those equations. This is a projectile that's launched at an upward angle, and so we saw that when you customize those equations, you end up with what's in this little orange box here, and these are the equations that we're going to use to work all the different parts of this problem. So let's get at it. So part A asks for finding the time to reach the top of the path. Now, projectile motion problems can be worked by a process of elimination once you have your customized kinematics equations, which are what we have over in this box over here. So basically what you do is you just pick an equation. Pick any equation and see if it helps you reach your goal. If not, move on to the next one. It's rare that this will ever require more than 2 steps. That is, if you go through all the equations and you don't have what you need, go through them again and you'll be able to find something that you need in one equation that you can plug into another equation. So let's see how that works just by working through all these different problems. Now, the problem that we want to find is the time it takes to reach the top of the path. And so we can look at these problems and we can say, this equation does not help me at all. The first equation, Vx, does not help me because there's no time. I'm looking for a time, so I need an equation that has time in it. So my Vy, this is something that I'm going to look at as possibly helpful because I do know what Vy is at the top of the path. So we want to find the time it takes to get to the top of the path. Do I know the velocity in the y direction at the top of the path? I do. What is it? What do you think it is? Say it out loud. It's 0. Why is it 0? Because as this thing goes up and down, the y component of the velocity has to reverse direction at the top. And so the velocity in the y direction has to be 0. Now, be aware, there's still an x component to the velocity at the top. So the velocity at the top of an arc like this is not 0. It would be just v naught x. That would be the velocity at the top. But the y component at the top would be 0. And so I know that Vy is 0. I just calculated what V naught y was. I know what g is. And so I can find the time. So here's that equation. We have Vy is equal to V naught y minus gt, and we set it equal to 0 because we know that this guy goes to 0 at the top. And so it's simply at this point plugging in the values that we know. There is my v naught y, there is my g, that's my v, my vy. I can solve this equation algebraically for t, and I end up with t equal to 1.97 seconds. What is that? That is the time to reach the top. And that's 1.97 seconds. And also, notice the units. I've got meters per second divided by meters per second squared. And so you'll get a lot of cancellation there, and you'll see that this meter cancels with that meter, that seconds cancels with one of the seconds there, and so your units are 1 over seconds, and that just becomes a unit of seconds. And so our time works out with the correct units, and our value is 1.97 seconds. Okay, the next part of the problem asks us to find the maximum height. And so which type of thing is height? Well, we know that that's a y. And so if we look at the y equation, which we have customized, it's v naught yt minus 1/2 gt squared. Now, we're looking for yf. Do we have everything else? We've got v naught y. We just found t. We know little g. So we can plug all those values in and just multiply them all out. And when you do that, you find that yf works out to be 19.0 meters, and that is the maximum height. Now technically what we did was we took the time that we found 1.97 and we plugged it in here. So that's the height at 1.97 seconds. But we found previously that that's the time when the y component of the velocity goes to 0, and we know that's when it reaches the maximum height of its path. So the maximum height, 19 meters. Now, the next part of the problem, part C, was to calculate the time it takes to reach the bottom of the cliff below. So we have our cliff here, and this projectile is launched up, and it's going to reach the bottom below, and we want to find out how long it takes to reach that time. So we can just start picking our equations, and we'll use the process of elimination. So this equation doesn't even have time in it, so we can't use that equation to help us. This equation has time, but what would Vy be? Vy would be the y component of the velocity that it would have when it hits the ground. And we don't know that. It's not given in the problem, and it's not something that we can obviously figure out. So that equation isn't going to help us. What about the next equation? We look at that one. We can say x is equal to v naught xt. We don't know what x is. X would be the horizontal distance that it travels. We don't know what that is. In fact, one of the problems is to calculate that. So that equation won't help us. Now, what about this? Do we know the y position at the bottom? That's what y is. We do. In fact, we know that that's that minus 100 meters. And we know v naught y because we calculated it. We know g. And so this equation has everything that we need to solve for the time. So all we have to do is take the y equation and plug in the variables that we know. We know the y final is minus 100 meters. We know the v naught y. We calculated that to be 19.3 meters per second. We know g is 9.81. And we can see that this whole thing is a quadratic equation. It's got a t squared term, a t to the 0 term. That means a term that's just a constant. And so if you have a quadratic equation, you can simplify it. I multiply 1/2 times 9.8, that gives me 4.9. I can solve this using the quadratic formula. Now, as a general rule, you can go ahead and plug the variables into the quadratic formula, but I have found that when my students try to do that, they very often will make sign errors. And one thing that can help prevent that is to put the equation in standard form. And that means to move everything over to one side and set it equal to 0. And you want to move everything over to the side that makes the t squared term positive, or the squared term in the quadratic equation. You want the coefficient of that term to be positive. If I'd moved everything over onto the right-hand side, this would be negative. But I moved it over to the left so that it would be positive, and then I moved everything else over to the same side. And then this is a quadratic equation of the form a t squared plus bt plus c equals to 0, and I can take my coefficients a, b, and c and plug them into the quadratic formula. Now, one thing to be cautious about, c in this case would be not 100 but minus 100, and b would be minus 19.3, and then a would be positive 4.9. Remember, you always want the a to be positive, so move everything to the side that makes a positive before you apply the quadratic formula. So we have our equation in standard form here, and we just apply the quadratic formula to solve for t. And so t is going to be minus b, so that's minus 19.3. That gives me a positive 19.3. And then I've got 19.3 squared, that's my b squared. Technically, it should be minus 19.3, but if you square a minus sign, it becomes positive. So I'm a little sloppy with that sometimes because it just doesn't matter. I'm okay with you're a little sloppy with it too, but you want to make sure that you understand what it is that you're doing, not just doing it. And then I have minus 4ac, that's the next part under the radical. The 4 is there, the 4.9 is our a term, and then the c is my minus 100. Well, again, I've got a minus times a minus, which makes the whole thing plus. And so when you square this out and multiply these together, you get t is equal to positive 19.3 plus or minus the square root of these numbers, all divided by 2 times 4.9, which is our 9.81 that we got. And then when you apply the quadratic formula and you simplify, you get two roots. You get 6.89 seconds, or you get minus 2.96 seconds. Now, it doesn't make sense to have a negative time in this problem, so we know that that can't be the right answer. This projectile is launched off of a cliff, and it's landing down below. It doesn't make any sense to say that that time happens at minus 2 seconds. So it's got to be the 6.89 seconds. That has to be the root that corresponds to when the object is on the ground. Now, I want to just pause for a moment and explain where that negative solution comes from, because it does actually have a meaning. It's just not physically meaningful in this problem. So imagine a completely different problem. I'm going to go off on a tangent for a little bit, but stick with me because I think it'll help make things make sense. Imagine we're not on a cliff, we're just on level ground, and we shoot a projectile up and it comes down. And so let's say I want to find the time when the height is here. So let's say that that's 5 meters or whatever it is. And so I want to know, when does it reach 5 meters? And so I would have my kinematics equation, y equals to v naught times t plus 1/2 a sub y t squared. Of course, that's going to be minus g. But our y would be 5 meters, and again, we would have a quadratic equation, and you would solve for t, and you would find the time that when it was 5 meters would be there, but you would find a second time when it was 5 meters that would be there. So it would reach, the first time it's going up, it reaches 5 meters, and then it would go up to the top, it would come back down, it would hit that 5 meter height again at a second time. Now, if this is a projectile launched from a cliff, there's no way, so if I picked a height here, the second time would be physically meaningful. But if I pick a time where it hits the bottom down here, the projectile was never at the other location where that quadratic equation gets solved. And so that's what we mean when we say it's a non-physical solution. So I hope that makes sense. The idea is just that that time, that minus 2 seconds or whatever it was, that would be the time if this projectile were traveling backwards along the full arc of the parabola, rather than the portion of the parabola that it actually goes on. So let's move on to the rest of our problem. We have part D. We want to find the velocity vector with which the projectile hits the ground. Now, I used to ask this problem and I say, what's the speed at the ground? And people would tell me 0. And so yes, when it hits the ground, it's eventually going to stop. It may bounce a few times, but that's not really what the problem was intended. What I meant was, what's the speed it hits the ground with? And so just be aware of that that's what we're looking for. And so we know, we just solved, it takes 6.89 seconds from the time the projectile is launched to the time it hits the ground. So all we do is we take that time and we plug that value into the velocity kinematics equations. And that'll give me the velocity at that time. And of course, after the ground is hit, like I was mentioning, our equations no longer work because the ground will change the way the projectile is being accelerated. In other words, the acceleration is no longer constant once it hits the ground, so the kinematics equations don't work anymore. Okay, we already found the y component of the initial velocity. We can also do the same thing to find the x component. We know that when the projectile was launched from its initial height, it had a x component. This would be my v naught. This would be my v naught x. This would be my v naught y. And this would be the angle that the initial velocity makes with the horizontal. And so my v naught x is along the adjacent side of that triangle, so it goes with the cosine. I plug in my values, and I find the initial velocity in the x direction, or actually you might want to say that as the x component of the initial velocity. So the x component of v naught. And so that's what we're going to need to find what the velocity is at the bottom. Now, one thing that we want to remember is that from our kinematics equation, we know that Vx is equal to V naught x, and that's constant. Because there's no acceleration in the x direction, the velocity that we got here, that's not just the x component of the initial velocity, that is the x component of the velocity always throughout that entire motion. So at every point on that parabolic path, the x component of the initial velocity is the x component of the velocity at all of those times. Okay, we just found the x component of the velocity when it hits the ground. In fact, we found the x component of the velocity at all times, when it's shot, when it's in the middle of the trajectory, and of course when it hits the ground. Now we want to find the y component of the velocity when it hits the ground. And so to do that, we're going to plug in the time that it takes to hit the ground. So we have that time there, and we want to plug in that 6.89 seconds. That was the time we calculated that it took to hit the ground. And so when you plug that in, you get that the Vy, that's the y component of the velocity at 6.89 seconds, the y component of the velocity when it hits the ground, is minus 48.3 meters per second. Now, that minus sign there, that shows us the direction. So if I think about that parabola for a moment, so the parabola, it shot off the cliff and it lands down here, we know that the velocity is going to be tangent to that parabola at that point, and it will have a y component and an x component. And so if this is my v final, this would be my v final x, and this would be my v final y, and it would be pointing down. And so that downward pointing component would have to be pointing in the negative direction. And so that's what we see when we do the math. The negative sign tells us that the component of the velocity at that time is pointing down. If I picked a time up here and found the velocity, I would find that it would have a positive component, but where we're looking at now, it has a negative component, and again, that is reflected in our answer. So now all we have to do is put those components together. The velocity when it hits the ground v is going to be that x component plus that y component, and of course the x hat and the y hat tell us the directions. And when we plug in those numbers, we get that v is equal to 5.2 x hat minus 48.3 y hat, and of course the units will be meters per second. And so that is the velocity that it hits the ground with. And that, of course, is the answer that we're looking for in that part of the problem. Now, the problem that I asked about didn't actually ask to calculate the speed with which it hit the ground or the angle that it hit the ground. But if it did, that'd be pretty easy, right? Because we know that speed, that instantaneous speed, is the magnitude of the velocity vector. So if I want the speed that it hits the ground with, I just simply have to take the magnitude of this vector, and of course I do use the Pythagorean theorem, and I would find that the speed with which it hits the ground is 48.5 meters per second. And of course I've drawn my little picture here, and I have theta would be the arctangent of the opposite over the adjacent, the 48.3 over 5.2. And if I take that arctangent, I find that I get 84 degrees. Now, that 84 degrees is, of course, there. But if you just write down 84 degrees on a test, I would count off because 84 degrees would be in the first quadrant. And so you can do one of two things. You can just simply indicate which quadrant you're talking about, or you could draw on your picture, you could draw a theta, and either of those would tell me that you know what angle you're talking about, and that would make me happy, and I won't count off. The last part of this problem was to find the horizontal range. That was the x distance. So this thing is shot off of a cliff, it hits the ground down below, and we want to know how far in the x direction it travels. And so we use our x kinematics equation. X is v naught t, and actually that should be v naught x times t. And we plug in our v naught x, and we plug in our t, and we get 35.8 meters, and that's how far it goes. And so I kind of glossed over it, but I actually made a pretty big mistake there. That v naught, that could be really confusing because v naught is not the same thing as v naught x, and we want to have the v naught x because this is the x equation. So even I make mistakes sometimes. You want to try very hard to be very careful about having the right labels for things, because if you just wrote v naught down on a piece of paper and then you went looking, okay, I know what v naught x was or v naught was, and you look and you see v naught, you might have written down not 5.2 but 20 or whatever it was, the actual v naught, and that would have given you a very wrong answer. So pay very close attention to those labels because they can be very useful. I'm tempted to say that I made that mistake on purpose just so I could show you how important it was to keep the labels of things right, but really I just screwed up. I forgot to put it in. But anyway, it was easy enough to catch, and so hopefully it will be easy enough for you to remember to keep track of your labels and to be very careful with them.